So this is the Chapter 6 lecture on thermochemistry. We're going to start with some definitions. If you break down the word thermochemistry, thermo kind of sounds like thermometer or heat. The technical definition of thermochemistry is the study of the relationships between chemistry and energy. You can also think of it as the study of heat transfer or heat movement during chemical reactions. What we're going to look at is when a certain chemical reacts, where does the energy go? Energy is the capacity to do work. So, for example, you need to eat food because the food you consume is converted into energy for you to do daily processes. Energy can be transferred through heat. By definition, heat is the flow of energy caused by a temperature difference. Remember that temperature, by definition, is the average kinetic energy of the particles. Energy is actually something an object possesses. For example, the reason why we haven't been able to get rid of or change from fossil fuels like gasoline is that gasoline inherently carries a lot of energy in its bonds. So when we burn gasoline, we get a lot of energy compared to the amount of gasoline that we need. And things like biofuel just don't have enough energy in their bonds for it to be a logical transition from fossil fuels to biofuels. Even though energy, heat, and temperature seem like they are the same thing, they are in fact different. Work is the result of a force acting through a distance. It's a way that an object exchanges energy. In physics, when we talk about work, generally we mean, for example, taking a block and moving it from one position to the other. And a little bit we're going to talk about why that definition doesn't really work in chemistry. There are two main types of energy. There's kinetic energy and potential energy. The word kinetic means movement. So kinetic energy is the energy associated with the motion of an object, and potential energy is the energy associated with the position or composition of an object. So the whole potential is the energy from position, and kinetic is the energy from moving. Definition works more with physics. It doesn't work as well when we talk about chemical terms. So you can think of it more as thermal energy is the energy associated with the temperature of an object, and that is kind of the synonym of kinetic energy for chemistry. So more often we're going to use the word thermal energy instead of kinetic, but remember, it says thermal is the energy associated with the temperature of an object. Temperature is a measure of the motion of particles. So you can see how that relates to kinetic. And potential energy, we're going to talk about in terms of chemical energy, which is the energy possessed in the bonds between electrons and nuclei in atoms and in compounds. So chemical energy is something that's stored within bonds, and then when the bonds are broken, energy is transferred. The classic kinetic potential energy diagram, again, this is more used in physics, but it's here. When you're going up a hill, this is also sometimes the roller coaster, you are storing more potential energy, and then when you go down the hill, the potential energy is going down and the kinetic energy is going up because you're moving. We're going to look at a couple laws of science here, laws of chemistry, laws of physics. The first one is the law of conservation of energy. We've talked about the law of conservation of mass. We've talked about the law of conservation of matter. Now we're going to talk about the law of conservation of energy, and they all generally follow the same definition. The definition of this law is that energy can be neither created nor destroyed. It can only be transferred into different forms. What we're going to talk about a lot is the system and the surroundings. The system is the actual reaction. The surroundings is everything else. What makes studying thermochemistry difficult is that it is really impossible to measure the temperature change of the system, of the reaction. Remember, the reaction is taking place really at the bonds, at the position of the electrons and the protons. And since that is so small, we don't have equipment that can actually get some kind of device in there to measure the temperature change. So what we do is we measure the temperature of the surroundings, and that gives us, because of the law of conservation of energy, information about the system. So if the surrounding changes by a certain temperature, we assume, because of the law of conservation of energy, that the system has changed by the exact opposite amount. So for example, if the surrounding temperature goes up, we assume the system temperature went down by the same magnitude. Next, we're going to talk about units of energy. We use the kinetic energy equation to get the units of energy. Remember that Ke equals 1/2 mv squared. M is for mass, V is for velocity. So when we look at the unit for energy, we're going to use a joule, Joule. The abbreviation is just a J. And we're going to remember that 1 joule is equal to 1 kilogram per meter squared second squared. The kilogram part is the mass part of the kinetic energy equation, and the meter squared per second squared is the velocity part. This is going to come into play if we ever are going to use math in some of these problems. The mass has to be in kilograms for you to be able to use a joule. Because a joule is a very small amount of energy, we often use kilojoules, KJ, and just like any kilo conversion, 1 kilojoule is equal to 1,000 joules. There are also some other energy units that you may see. A calorie is used a lot of time in food consumption. That's usually on what's on the labels of your food. Now, this is a little confusing, but a kilocal, which you would think would look like this with the kilo and the calorie, is equal to 1,000 calories, but what you see sometimes is a capital C versus a lowercase c. So if you're doing a problem, you can't figure out why you're off by a number of decimal places, it's probably this. A kilocal naturally or usually is indicated by a capital C, and that just stands for 1,000 calories. And finally, a kilowatt per hour is usually what electricity is measured in. If you go out to the side of your house where the meter guy comes and reads your meter, that's measured in kilowatts per hour. And you can see all the conversions to joules here on the side. We're now going to introduce the laws of thermodynamics. These are used in both chemistry and physics. The first law of thermodynamics is that the total energy of the universe is constant. Because we know that energy is not created or destroyed, the universe does not exchange energy with anything else. What we basically say is when the Big Bang happened, that was the creation of all the energy that exists in the universe. And all that's happening is all the processes that happen in the universe is just a transfer of energy. So every time a star dies, that energy is released, and then that energy is used to make a new star or a new solar system or a new planet. Everything's always cycled. It's always a big cycle. The energy is not going to go anywhere. This is why the perpetual motion machine cannot exist. The perpetual motion machine is kind of a classic science thing that comes up where people say they've discovered this. Basically, what it would be is a water wheel that would constantly move. You wouldn't lose energy anywhere. This is not true. You cannot get a perpetual motion machine. Internal energy, abbreviation is E, of a system is the sum of the kinetic and potential energies of all the particles that compose the system. You can think of E as the inherent potential of the particle. How much energy does that particle have with it because of the bonds? We say that this is a state function. This is kind of like a checking account. What it means is the value depends only on the state of the system, not how the system arrived. So we don't care, if we're talking about a bank account, how many deposits you made, how many times you spent money. Really what we care about is what was your balance at the beginning of the month and what was the balance at the end of the month. There are specific parameters for internal energy, including temperature, pressure, concentration, phase of matter, and we're going to see all that later in this PowerPoint. The value of a change in state is a function of the difference between the final and initial value. So you can look at our equation here. Delta E, remember delta means change. So the change in energy of a system is equal to the final energy minus the initial energy. In a chemical reaction, the reactants are the initial state and the products are the final state. That is just how it works. So you can take the equation that we just looked at here, finest minus initial, and insert these two new values, and you get the total energy is equal to the energy of the products minus the energy of the reactants. Now remember we talked about it. We cannot measure usually the energy change of the system. So what we do is we measure the energy change of the surroundings. And according to the first law, the amount of energy lost by the system must exactly equal the amount of energy gained by the surroundings. So delta E of the system should equal delta E of the surroundings. If the reactants have a higher internal energy than the products, delta E is negative and the energy flows out. If the opposite is true, if the reactants have lower internal energy, delta E is positive and the energy flows in. We're going to talk a lot about signs in these chapters. The sign is very important. You're going to remember that whenever you see a negative sign, it always means outward. Something is going out, something is happening on the outside. And a positive sign is always meaning inwards. A system can exchange energy with its surroundings through heat and work. And according to the first law of thermodynamics, the change of E of energy of the system is the sum of the heat transferred and the work done. Transfer of heat, pure transfer of heat, not how much heat something contains, that's something different, but how much heat is actually moved. The symbol for that is a Q. And then we've talked about work before, which is a W. So to get the internal energy of a system, you add Q plus W. Again, a positive sign of E means energy is going in. A negative sign means energy is going out. So we can look at some other sign conventions for Q, E, and W. But in general, if you always remember, positive always means in, negative always means out. So for Q, if Q is negative, the system gains energy. If Q is positive, I'll switch that. If Q is positive, the system gains energy. Negative, it loses energy. For work, we're going to define it slightly differently, but it's still going to fall under the same parameters. A positive sign for work means work is done on the system. Negative means it's done by. And delta E, the change in internal energy, again, positive, it's going to flow in. Negative, it's going to flow out. Heat is the exchange of thermal energy between a system and its surroundings. We talked about that definition. And then temperature is a measure of the thermal energy of a sample of matter. Remember, it's how fast the particles are moving in a certain sample. We do get to a state of something called thermal equilibrium, where the heat transfer is going at the same rate. Basically, heat always moves from warmer to colder. So once you reach a certain point where that heat exchange is even on both sides, the net movement of heat stops and you reach thermal equilibrium. There's no additional net transfer of heat. This is very similar to water transfer and osmosis and other things we've talked about. Equilibrium is when the heat exchange has gone to zero. Heat capacity is a measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. You can think of this as it's going to stay the same temperature to a certain extent as you add heat, very much like oven mitts. Oven mitts have a high heat capacity because you are able to heat them to a high temperature degree before they actually change temperature themselves. The formula for this is Q equals C, which is a heat capacity as a constant, times delta T, which is the change in temperature. C is a value that you would look up much like density. So each individual substance is going to have a C value that you would either have to be given or look up. C is usually defined as the quantity of heat required to change the temperature by 1 degree Celsius. The unit for C is the unit of heat divided by the unit of temperature, which is a joule per degree Celsius. Specific heat capacity is a little different. This is the measure of the intrinsic capacity of a substance to absorb heat, or the amount of heat required to raise the temperature of 1 gram by 1 degree. You see these two definitions are very, very, very close. Maybe you look at specific heat capacity gives you a unit of actual amount, a gram. The units for C are joule per gram per degree Celsius. Molar heat capacity is the same thing, but instead of gram, you're going to use a mole. The specific heat capacity of a substance can be used to give you a number relationship between the amount of heat added and the amount of substance and the corresponding temperature increase. So if you look at, to get the total heat transferred, you're going to look at the mass times the specific heat capacity times the temperature change. So to calculate Q, heat transferred, you're going to do M times the specific heat. Remember, that's a value that's either going to be given or you're going to look up, times the change in temperature. We looked at before the definition of work, which is force by distance. But in chemistry, since we're using such small things like electrons and nuclei and protons, the whole moving a distance doesn't really work. So what we pay attention to in chemistry is pressure and volume. We kind of call it pressure and volume work. It's work that is done to the volume change as a result of force. The work caused by an expansion of volume is the negative of the pressure that the volume expands against. That's just giving you the definition you see at the bottom. So instead of the work formula being work equals force times distance, we're going to say work equals negative P delta V. So work is equal to negative pressure, whatever the pressure is in that time, times the change in volume. The system's going to exchange energy with its surroundings via heat and work. So you can see here's the heat equation we did, and here's the work equation we just looked at. Calorimetry is the process where you measure this heat exchange. So if you force the energy change of a reaction to appear as heat rather than work, you can just measure the change in temperature and figure out how much heat was exchanged. So if a reaction is carried out at constant volume, remember that would mean the work is zero. The heat evolved is equivalent to the delta E. So if we look at the equation, delta E equals Q plus W. If work is zero, because the volume zero, work's going to be zero, then the delta E of the reaction is just going to be equal to the Q. Calorimetry is when you measure the thermal exchange of heat between the reaction and the surroundings. A bomb calorimeter is a piece of equipment designed to measure the delta E for combustion reactions. The key to calorimetry is keeping the volume the same, because when you do that, when you keep volume the same, the work becomes zero and Q then equals E. So the magnitude of delta E, the magnitude of the change in temperature is going to be directly equal to the magnitude of the change in energy. So Q is going to equal C times delta T. This is a bomb calorimeter that we just talked about. Basically, you would have the reaction going here. You're going to have the volume of water constant. You're going to have a temperature measuring the change. You're going to have this stir, so all the heat is exchanged. And this is going to tell you something about what happened in this cup here. Since that's a very highly technological piece of equipment, we can use something called a coffee cup calorimeter, which is basically just a styrofoam cup. Remember, styrofoam is a thermal insulator, which means it's not going to lose as much heat to the environment. And you're going to have a reaction that's conducted in water. You're going to have a stirring rod to make sure the heat is constantly moving, and then just a thermometer. And what you can do is just measure the temperature change, and that'll give you an idea of what the energy change was. This picture just compares the two types. The bomb calorimeter really keeps the volume very constant, and the coffee cup keeps the pressure constant. Either way, the work is going to be zero, so the delta E is going to directly equal the delta Q. Delta E reaction measures the total energy change of both heat and work. When you are only interested in the heat exchange, you use enthalpy. Enthalpy is a different term, it's a different value than delta E. Enthalpy's symbol is H. Enthalpy of a system is the sum of the internal energy and the product of its pressure and volume. So H is going to be E plus PV. The change in enthalpy occurs under constant pressure. So delta H equals delta E plus P delta V. Since delta H is equal to QP, you can sub that in here. So this equation is what E equals. E equals Q plus W, so I've just substituted that in. And P delta V, again, is equal to work. So if you look, delta H equals Q plus W minus W. You can get rid of this. So delta H just equals Q. Both delta H and delta E represent changes as a state function. Remember, it doesn't matter the process. It doesn't matter the steps you take. It only matters where you started and where you ended. Delta E is a measure of heat and work. Delta H is a measure of only the heat exchange under constant pressure. Again, very, very close definitions, but they're not quite the same. For chemical reactions that don't exchange much work with the surroundings, meaning there's no large change in volume, delta H and delta E are nearly identical. And this is what's going to happen most of the time. Because there's not going to be a large amount of volume change, delta H and delta E are going to be pretty much the same number. When chemical reactions produce or consume a large amount of gas, delta H and delta E are going to be slightly different. We're going to use a lot the term endothermic. If you see an endothermic, endo always means in. So an endothermic reaction absorbs heat from the surroundings. You're going to have a positive delta H because the heat's going to flow in. We've seen that a million times, that when you see a positive sign, something's going in. An example of this would be an instant cold pack. That's those things you had probably when you're playing sports where you have the little bubble that you squeeze um, and it gets colder. Exothermic, exo means exit or out. This is going to give off heat to the surroundings. Again, negative always means out. Heat's going to flow out. And this is any kind of combustion reaction. The emitted thermal energy doesn't come from the original thermal energy, it comes from the potential energy contained in the bonds. So when you're burning gasoline and it's releasing energy, the energy it's releasing is coming from the breaking of the bonds. And remember, that is a specific quality of that compound. There is a limit to how much energy is contained in that compound, and that's why we use certain things as fuel and other things don't work as well. We can actually have stoichiometry become involved here with these problems. The enthalpy of a reaction or heat of a reaction is an extensive property. The amount of heat generated or absorbed depends on the amount of reactants that are there. Obviously, the more you have, the more heat's going to be produced. Delta H reaction is specified with a balanced chemical equation. So if we look at this equation here, the magnitude of delta H reaction has to either be looked up or given. This is not something you would memorize. So what you see here is a combustion reaction of C3H8. You can see the CO2 and H2O. It is balanced. And this is going to be given that the delta H of this reaction, when you burn C3H8, you're going to get 2,044 kilojoules out. You're going to get heat going out. The reason I know that is because right here, this negative sign tells me that the heat's going out. So this means that when you have 1 mole of C3H8 reacting with 5 moles of O2 to form 3 moles of CO2 and 4 moles of H2O, you're going to get 2,044 kilojoules of heat coming out of that reaction. So the way you can use the stoich is figuring out, okay, well, how much heat comes out if you have 2 moles or 3 moles or 50 grams? You can use the stoich to figure that out. And a chemical equation is multiplied by some factor, the delta H is also multiplied by that factor. So for example, we just said, if you have double the amount of that compound, then the delta H, the amount of heat that comes out, is going to be doubled. So whatever you do coefficient-wise to the compound, you're going to do to delta H. If the chemical equation is reversed, then the delta H gets reversed. So if it's coming out originally, you're going to switch it, and you see it's flipped here. So first you have A plus B yielding C. You can see here the equation flips. Well, then the delta H sign flips because you're doing the opposite reaction. Hess's law is a way to add delta H's for a multi-step process. What you're going to do is you're going to compare the steps in a reaction and then look at the final equation. And whatever changes have been made to each step, you're going to do the exact same change to the delta H. And this is called Hess's law. That's the change in enthalpy for a stepwise process is equal to the sum of the enthalpy changes for the steps. So you can see here, this is the first step that happens, and here would be the value of delta H. Here's the second step, here's the value of delta H. To get the total delta H, you would add those two together. So if we look at example problem, the following reaction between carbon and water is an industrially important way to generate hydrogen gas. So what it's asking is, here is the actual equation, the final equation. How much heat comes out of this? And here are the stepwise processes. You would be given all this in a problem. So you have each step, basically each thing that's formed, and how much heat is either generated or used in that process. So what I'm going to do is I'm going to compare these to the final equation, and whatever change, I'm also going to change that in delta H. So if we look, since the first reaction has carbon as a reactant, and the reaction of interest also has carbon as a reactant, we're just going to simply write that unchanged. There is no flip, there is no addition of a coefficient, nothing really changes, so therefore nothing changes with the delta H. If you look at the second reactant, there is actually 2 moles of CO instead of 1, and the reaction has flipped. So we're actually going to do two things to this delta H. We're going to cut it in half, and then we're going to flip the equation, which means we're going to flip the sign. The third reaction has H2 as a reactant, and the reaction of interest, however, H2 is a product. Therefore, we're going to reverse the equation and reverse the sign of H. In addition, to obtain coefficients that match, you're going to cancel out the O2, which means we're going to multiply the reaction and H by 1/2. So lastly, we rewrite the three reactions after multiplying through, making all the changes. So we're going to flip things, we're going to add and multiply with delta H, and then simply to get the final delta H, you just add all the subsequent steps together. A standard heat of formation is kind of like, whenever you hear the word standard, it's always a base. So since we are interested in changes of enthalpy only, we are free to define the zero of enthalpy as convenient and possible. And this is called standard heat of formation. It has three parts: the standard state, the standard enthalpy change, and the enthalpy of formation. So we look at the standard state. That just means what state is this thing in at this certain standard condition. So the standard state for a gas is a pure gas at a pressure of exactly 1 atmosphere. If that system or that substance is a gas at 1 atmosphere pressure, we're going to say that's its standard state. For a liquid or a solid, the standard state for a liquid is the pure substance in its most stable form at 1 atmosphere and at what temperature you're looking at. And in solution, the standard state is when it's at 1 molar. The change in enthalpy for a process when all the reactants and products are in their standard state is called the standard enthalpy. The way you're going to see the difference between regular enthalpy and standard is this little degree sign. Whenever you see that degree sign, it means standard. And that's going to tell you right away, instead of calculating delta H, you're going to look it up from a chart. It's a standard. It's a given. It's a basic. It's something that everybody knows. You're going to go into a chart and you're going to find the delta H for that reaction. If you're a pure compound, the change in enthalpy when 1 mole of the compound forms is equal to its constituent elements. For a pure element, the delta H is going to equal 0. You can measure all changes in enthalpy of the pure elements relative to this standard state. The standard heat of formation is the third thing. Notice the little F. It still has the degree sign for the standard, but F is for the formation part. The standard heat of formation corresponds to the formation of the compound from its elements in their standard states. So if you have, Na and Cl coming together to make NaCl, that would be the formation, how much heat it takes to make that. The negative of the standard heat of formation corresponds to the decomposition of the compound into its elements. You can calculate the enthalpy change of a reaction by mentally taking the reactants through the two steps. First, they decompose the reactants. Second, they form the product. So again, kind of like Hess's law, this is what happens to the delta H's, and then to get the total delta H standard of a reaction, you add those two together. So for example, calculate the standard enthalpy change for the combustion of methane. So here's my equation, my final equation, and I want to know what is the enthalpy of formation, how much heat is formed with this. The first step is the decomposition of 1 mole of methane into its constituent elements in their standard state. So what's going to happen is methane, CH4, is going to break down into carbon, which is a solid form, which is graphite, and H2 gas. The reason it's H2 is because it's hydrogen, and hydrogen has to be diatomic, and the 2 just comes from balancing. So the change in enthalpy for this step is obtained by reversing the enthalpy of formation equation and changing the sign. The second step of formation of the products from their elements, first you're going to get the formation of CO2, and then you're going to get the formation of H2O. Since the second part forms 2 moles of H2O, the delta HF for that step must be multiplied by 2. You can see this is very similar for Hess's law. From Hess's law, the enthalpy of reaction is the sum of the enthalpies of each individual step. So we look here, we're going to do all the manipulations of delta H that we need, and then finally we're going to add them together to get the total. To calculate the delta H of a reaction, you subtract the heats of formation of the reactants, multiply by their stoichiometric coefficients, from the heats of formation of the products, multiplied by their coefficients. So to get delta H of reaction, you're going to get the sum of, that's what this symbol means, the products times the delta H of formation minus the delta H of formation of the reactants. N stands for the coefficient. So N, this is supposed to be sub P, represents the stoichiometric coefficients, and T is the reactants, and F is the products. And finally, the energy use and the environment, which is going to deal with fossil fuels, is in your textbook. So go ahead and please read that section, the last section from this chapter in your textbook.